Good day, folks. This is tutorial number 4 in a playlist that's designed for people who want to use the 3D Experiences FEA solver, which incidentally happens to be the Abacus program, in order to solve certain problems. It is important to mention that the interface of the Abacus within 3D Experience is completely different from the one that's in Abacus CAE. And in fact, some of the functionalities are different too. So this series of tutorials is actually very useful for people who want to transition from Abacus CAE to 3D Experience or entirely new there. So what I do is I pick tutorials which are done with the Abacus CAE on YouTube in its entirety and replicate the steps in the 3D Experience platform. Uh, the particular tutorial that we're going to be doing is, I recently saw it in that site below, in that channel below, and it's very good, except that they use the constraint equation to solve the problem, okay? And constraint equation is not directly available in the menu uh, uh, features of the 3D experience, so we have to do it differently. The problem that's being looked at is you can think about it as a steel plate with a bunch of holes in it, like that. And uh, the ends of this plate are being pulled up by some amount. So when you think about it, essentially, as long as you stay away from the ends of the edges, each one of these will almost behave the same way. So all you have to do is to look at the analysis, do the analysis is one of these, which is called representative volume element, and uh, do this, and then apply the law. Now, there are a couple of things that you have to realize. First of all, uh, the tutorial below uses the plane stress condition in order to solve this problem. We don't have 2D elements such as plane strain, and plane stress in the 3D experience, so we're going to solve it as shell element. Shell elements, in case there is no lateral load, is going to be essentially a plane stress condition. Now, I refer to it as doing a steel problem with a bunch of holes, but that is really not the kind of thing that this is used for. It's used, for example, in composites and composite material, and you have to essentially extract a unit cell out of that. And the unit cell can be either the one that I'm looking at in this tutorial, or it can be like that. Okay, and that's why it's called RVE, representative volume element. Okay. Now, I will be using the same information that the fellow is using in his tutorial. So the size of the square is 2 millimeter by 2 millimeter. The radius of that circle is 0.3 millimeter. It's made out of this rather soft material, 100 megapascal Young's modulus and Poisson ratio 0.47. But I will be doing analysis, assuming a material behaves in a linear elastic way, but it really doesn't matter. So this edge is being pulled up by 0.3 millimeter. These are roller support essentially, and that edge must remain flat. And this is exactly the crux of this tutorial. How do you make sure that this edge stays flat? And the way this is handled is by we create a master node down here, a set here, which represents that single node. And these nodes are supposed to follow that master node, followers, and in the horizontal direction. So this is a master node, these are follower node, and in 3D experience, as I said, there's no constraint equation functionality, so you have to use coupling here. And when you click on the coupling, it asks you for two sets that essentially one is the master, the other one is the follower. So what I do is the master node, I'm going to put it in a certain node set. In 3D experience, it's not called set, it's called group. And the follower nodes, those nodes above it, I'm going to put it in a different node, different set or different group. And it's important that they follow, these followers move in the y direction the same way that the master one does. So this is checked, and it's very important that this be checked. If not, so we don't have a reference point here. We have nodes following each other essentially. I'll show you what happens if you take this off. Now, these are my two sets, and I will be using this kind of a mesh distribution, although it's not really relevant to the problem, but I will use this information. Okay, so let's go ahead and do that. So there we are. We start with the part file. And on that vertical plane, I will sketch my rectangle or square, 2 millimeter by 2 millimeter. Let me make this thing. So this is 2 millimeter. And I'm going to make this also 2 millimeters. Good. Exit. Okay. Now, because we're using shell elements, I'm going to put a surface here. So obviously you have to go to generative shape design to do that. And I'm going to fill this thing, surface, fill it with, fill it with, fill that. Okay. And I will draw a circle of that face. Of that face, I will sketch a circle of radius 0.3 millimeter. Radius 0.3 millimeter. I'll change this thing to 0.3 millimeter. There we are. Exit. And I will split that. Transform. Split that surface with that circle. There we are. Okay. Now let's go ahead and apply our material. So we go to Tools, create a material, RVE, July 31, 2025. Okay, say all right. I'm going to apply this thing. Actually, all I have to do is to take this thing and put it on that. Make sure you check the green box so that material is put in there. Now, there's no information, so I go and input my information right now. Double click on this. Under structural, under abacus, under mechanical, under elasticity. Elastic, this is 100 megapascal. Young's modulus is 100, and Poisson ratio is 0.47. Okay, good. All right. Now we're done here. We're going to go and do the meshing. So go to my application, which is structural model creation, MTFEM. Okay. So under meshing, I will select that surface, and it's a surface quad mesh, and it's linear right there, and the size of it is right there, or 0.2 millimeter, which this is 0.2 millimeter. Actually, yeah, let me leave it like that. Okay. Now, I want to put a seeding around these edges, so I click on Edit. These are unnecessary, but I think it's helpful to do it. So under seeding, notice that it shows you the seed based on those dimensions. So what I'm going to do is I'm going to select, for example, this number 10, edge distribution. We put down 20 here, green check mark, and do the same thing there, 20, green check mark, 20. You can see how it different it is from abacus. 20, green check mark. And then this one is the circle in the middle. Zoom in here a little bit. 30. 30. Green check mark. Okay. Exit that. And now if you update, the mesh should show. Now there's a warning here because if you check it, it says there's something inconsistent about the sizes, no problem. So what I'm going to do is I will go to here to this. And I'm going to delete that mesh warning. That's okay. No problem. Now for section properties, shell section, select that surface, thickness 0.001. That's irrelevant. Material has been selected, and then we say okay. Good. Okay. I didn't like the fact that I got a warning there and had to go and delete that branch, but that's okay. Now we're going to select our group. See that groups on the groups tab? Groups. Click on it. For this one, I'm going to create a manual group. Manual group. I select this point, this node actually. One node has been selected, and I'm going to call this thing master. Master node. Node. Say okay. Now these other nodes here, I don't want to pick it one by one, so I'm going to look at the front view from the front, and then I'm going to use what is called on the group, I'm going to use a spatial group. So basically you make a box around these, except the last one. Don't pick the last one. The last one is already in the master group, so I'm going to call this thing follower group, follower nodes. And then we say okay. So we have two groups here, master node, follower node, and one of them contains, the master one contains one node, and the follower one is everything above that. Now, I think we are good with everything else here. So now we're going to go to our structural scenario creation. We select our finite element model. We select the procedure, static step, and by default, by default, the nonlinear geometric effect is selected, which is okay because the 0.3 upward displacement is relatively large. So, but I'm going to use the same information that the other YouTuber is using: initial time increment and the maximum time increment of 0.1. And this I leave it the way it is. So we say okay. All right. Now we're going to do the boundary conditions. The boundary conditions under fixed displacement. By the way, one thing I forgot to do was to create my coupling, but that's okay. We're going to do that. I forgot to do it. I'm sorry, but we're going to do that. Okay. So for support, I want to select this edge, but I can't do it. That's because basically that geometry is sitting on top of it. So we say hide it. Now I can select it. See that? I put the cursor here and say hide to take away that surface basically. So what is that? Support is that edge, and does not move out of plane, no translation in Z, and no translation in X. Okay, very good. Now I do the same thing for this edge. I can select it because remember I right click and hit the stuff that was blocking the selection. This no displacement in X and no displacement in Y, and then we say okay. Now I want to push this thing up, so we go to apply translation. We select that edge, upward direction of 0.3 millimeter. Okay, 0.3 millimeter. Good. Now the coupling, I forgot to do it. So how do I do that? I have to go back to the uh, basically back to let me show you. You go back to structure model creation. There is the interaction tab. Sorry, connections tab. Connections tab. You scroll down, select the coupling, and for support one, I select the master nodes or the group master node. For support two, I select the follower node. And these is a kinematic. This is very important. Kinematic. And I want them to move together in the direction Y. So all those follower nodes should follow this master node in the Y direction. Okay. Now, this is very critical. I'm going to check that. If I don't, you're going to get garbage. So let's say check this and come back. Once this thing runs, we'll come back and take this away and see what happens. Say, okay. So we're good. This is something that I forgot to do, but now we took care of it. So we go back to our scenario. And yeah, so that's pretty much it. So let's go ahead to simulation. Let's do a model and scenario check. It's always a good idea to do that. That's good. Simulation check to get any obvious and trivial stuff which is wrong. It may take a few seconds, but it's worth the try. And then finally, we're going to simulate, which means run. Okay. There's some stuff that I did that was unnecessary, that seeding stuff and meshing and things like that. I could have used the default even triangular shell elements. That's okay. All right, almost done. Very good. Close it. Now we're going to run it. And this thing better stretch upward, and that vertical right side remain a flat plane, a flat line. If you don't do that coupling, it will actually bow. Okay? You'll find out. This is doing a nonlinear calculation because of the fact that strain is large. Extracting results. All right. So, okay, very good. So let me close that. I don't want the first increment. You can see that this, let's check the displacement first. Displacement, okay. So notice that we can animate it actually. Animate. We reduce the speed here. See that line remains a straight line. And I'll show you what happens if I take that coupling away. And incidentally, if you look at the von Mises stress, you get about around 30, which is very close to what the fellow gets using the abacus. The intention is not here to compare or decide on accuracy. We just want to know how to do that. Now, let me exit this. And go ahead and take that coupling, away, so you can either take it completely away, or let's do that. So let's go here under engineering connection, right there, under coupling. You double click on it. If I take it completely away, it will bow in. And even if I see, if I change this thing from coupling node to reference point, which don't have any, and run it, if you go back to scenario and run it, you get garbage. And then I'm going to go and completely take it away and show you what happens. So this is when I took the wrong radio button. Obviously, this is not correct. Displacement. Obviously, this is not correct. This doesn't uh, look at the value of the von Mises stress, for example. Gigantic stress is over there. Okay, so this is nonsense. Now, what if I took that thing? By the way, this is a scale of 1. If you want to change the scale, double click on it. You can change the scale to something else, maybe 100. Okay, something like that. This is how to change the scale. Anyway, this is nonsense. So let's go ahead and take that coupling completely away. We go back to here. Okay. Let's delete this and now run. Let's see what happens. That radio button note has to be checked. This is taking the coupling completely away, and we're going to see how it looks like after deformation. It's not going to be a straight line. Okay, so let's actually go ahead and look at. I mean, basically, you get garbage, nonsense. Okay. And look at the deflection, displacement, views from the front. You can see it goes out. If you double click on it and change the scale to, for example, 10, you can see bows out, bows in actually. All right, folks. So that's good, critical, and we don't have access to the stuff that this fellow is doing in Abacus. Although the solver is Abacus in 3D Experience, but not everything is there. Not all the functionality is there. There are other ways of doing it. Good luck.